Hello everyone, welcome back. In this video, we will be covering summary of curve sketching. So after learning in chapter 4, all about graphs, how calculus plays an important role in finding where the graph is increasing, decreasing, concave up, concave down, how to find out the inflection points, how to find out the absolute maximum, absolute minimum, local maximum, local minimum, etc., etc. In this section, we are going to put all these things together, and then we are going to see how a comprehensive graph could be drawn. And now there are guidelines to that, just like the way you did algebra classes. Now we are going to involve first derivative, second derivative, test and all that to do a better comprehensive graph of a function. So even though all these guidelines are only guidelines, they need not be they need not always be, it's not necessary to follow all the guidelines like A through H in every single problem. Sometimes we will be able to get a good graph with 4 or 5 steps, but sometimes we may have to do more than 4 or 5 steps. So, but the guidelines are there. We will follow these guidelines as much as possible, as much as it's necessary for the problem. The following is a checklist is intended as a guide to sketching a curve y equal to f of x by hand. Not every item will be relevant to every function. The first point is about the domain. We always go with the domain of the function. What is the input for the function that we are going to graph? So the domain. Domain, the set of values of x for which f of x is defined. Next, we want the intercepts, the x-intercept and the y-intercepts. When you say x-intercept, you will set the y to 0. For the y-intercept, you set x to 0. Symmetry, whether the graph is symmetric with respect to y-axis, or is a graph symmetric about the origin, or is a graph a periodic function such like trigonometric functions, and so on. If f of negative x equal to f of x for all x in D, then f of x is an even function. If f of negative x equal to f negative of f of x for all x in D, then f of x is an odd function. If f of x plus p equal to f of x for all x in D, where p is a positive constant, then f is called a periodic function. And the smallest such number p is called the period. So this will be relevant to trigonometric functions, the last part. Then what are the horizontal asymptotes? We have seen how to find the horizontal asymptotes as x approaching infinity or negative infinity. What happens to the y value? Those are horizontal asymptotes. Find the horizontal asymptote. Find the vertical asymptotes. So set the denominator equal to 0, solve for x, solve for the variable. Or we also find out in terms of calculus, so the first one, horizontal asymptote, x approaching infinity or negative infinity, what happens to f of x? That is the horizontal asymptote. Now for the vertical asymptote, we try to do limit as x approaching a from the right or left. If f of x equal to infinity or negative infinity, then we say x equal to a is the vertical asymptote. We do that. Then slant asymptote, which means we perform long division, and then we take the quotient for that slant division, slant asymptote. The next we want to know where the graph is increasing, decreasing. The intervals of increase or decrease. Where the graph increases, where the graph decreases by using ID test, which is the first derivative positive. If the first derivative is positive in an interval, then f of x is increasing on I. If f of x, f prime x is, if f prime x is positive on I, then f of x is increasing. If it is negative on I, then f of x is decreasing. Right? So find the intervals of increase or decrease. Then we also find out the local max, local min. Find the critical points. This should be critical. Find the critical numbers of f, which means f prime c equal to 0 or f prime c does not exist. Then use the first derivative test. If f prime changes from positive to negative at a critical number, then there is a local max. If f prime changes from negative to positive at c, then f of c is the local minimum. You can also use the second derivative test as well. Then we also need to know where the graph is concave up, concave down. Concave up, concave down. Compute f double prime x for concavity test. We use the concavity test. If the second derivative is positive, then it is concave up, concave up. If the second derivative is negative, it is concave down. Inflection points occur where the direction of concavity changes. Then the last part, putting all these together, we'll be sketching the comprehensive graph. You can check your graph with the help of graphing calculator and just to make sure that you are on track. These guidelines are when we draw the graph by hand. So as I said earlier, it is sometimes necessary to follow through all the guidelines. Sometimes it's just not necessary to do all the necessary guidelines. With the minimum number of steps, we will be able to get the graph, the desired graph. All right. So here in this I've these additional suggested problems. This problem and this problem are already done in the videos of the section. Videos of the section has problem number 1 and problem number 9 are already there. So I'm going to be showing you for this video, we will focus on problem number 15. So this is the one I'm going to be showing in this video. Let's try that. So use the guidelines of this section to sketch the curve f of x equal to x square over x square plus 3. All right, x square over x square plus 3. We will start up with the domain. What is the domain? Domain is what are the possible inputs for the function, for the variable x, domain of the function. Or in other words, is there any value of x that you cannot plug in or which will make the function undefined? So no value of x can make the denominator 0. So the domain is all reals. Then we'll find out the intercepts. We'll find out the intercepts. So let's find out the y-intercept first. So for that, you set x equal to 0. So y equal to 0 square over 0 square plus 3 but 0 over 3, which is equal to 0. So y-intercept is x0, y0. Okay. All right. And what is the x-intercept? So x-intercept is obtained by setting y equal to 0. So 0 equal to x square over x square plus 3. This implies x square equal to 0, x equal to 0. So x-intercept is also the origin. So both x-intercept and the y-intercept are the origin. We know that all reals is the domain, and we have found out the x-intercept and the y-intercept. Next, let's try according to the guidelines, we have to find out the symmetry, which means whether the graph is symmetric with respect to y-axis or x-axis or the origin. So let's find out f of negative x, change the x to negative x. So then the function x changes to negative x. So negative x the whole square plus 3, which is x square over x square plus 3, which is same as the original function. So you notice that f of negative x is same as f of x. Therefore, the function is an even function. It is even, which means symmetric about the y-axis. By symmetric about the y-axis, we mean the branch on the right side of the y-axis is the mirror reflection of the branch of the graph on the left side of the y-axis. Okay, that is what it means. So there is a symmetry. So it is enough if you actually do one of the two sides of the graph. So if you reflect it about the y-axis, you will see the other side of the graph. That's the purpose of knowing the symmetry. Next, we are going to do the asymptotes. So let's start off with the vertical asymptote. Vertical asymptote, if you set the denominator to 0, so nothing makes the denominator 0. So there is no vertical asymptote. There is no vertical asymptote. Is there a horizontal asymptote? Is there a horizontal asymptote? So there is no vertical asymptote. Is there a horizontal asymptote? So for that we have to find the horizontal asymptote, we have to find out what happens when x approaches infinity of x square over x square plus 3. So to do that, you divide the numerator and the denominator by the highest exponent of the denominator, which is limit is x approaching infinity, 1 divided by x square over x square plus 3 over x square. So this will be limit as x approaching infinity, 1 divided by 1 plus 3 over x square. As x is approaching infinity, this is a very large number. So 3 over a large number will become 0. So it is just 1 over 1 plus 0, which is 1. So the horizontal asymptote is y equal to 1. So there is no vertical asymptote, but there is a horizontal asymptote whose equation is y equal to 1. What is the next one in the order of the guidelines? So find the intervals of increase or decrease. That is E, right? So find the intervals of increase or decrease. Intervals of increase or decrease. So for that, we have to find out the derivative. So f of x is in the form of a quotient. So we have to apply the quotient rule to find out the derivative, quotient rule. So it is the denominator, which is x square plus 3 times derivative of the numerator minus numerator times derivative of the denominator divided by denominator square. Okay. So it is x square plus 3 times 2x minus x square times 2x divided by x square plus 3 the whole square. So that will be, if you distribute, you get 2x cube plus 6x minus 2x cube all divided by x square plus 3 the whole square. That is f prime x. So 2x cube get cancelled. So it is 6x over x square plus 3 the whole square. So that will be our f prime x. So the denominator is always positive. So it is positive. The denominator is positive. The reason being, first of all, it's a square, and also inside the square, you have x squared plus 1. So it is doubly positive. So everything in the denominator is positive. So the sign of f prime x depends only on the sign of the numerator, which is 6x. So f prime x would be positive whenever x is positive. 6x is positive. In other words, x is positive. F prime x is negative when x is negative. So these two implies that f is increasing on 0 through infinity. F is decreasing on negative infinity through 0. Right? So we now know. We have found out several things about the graph. Domain first, and then what the y-intercept is, what the x-intercept is, then whether there is a symmetry, then what is the vertical, what is the horizontal asymptote, then when is it, in which interval is it increasing, and which interval it is decreasing. All right. Next, we have to do the concavity test. We can also picturize this increasing and decreasing. Like if you assume this to be 0 here, 0 through infinity, f is increasing, and decreasing on the interval negative infinity to 0. Right. So we have come this far. Next, we have to do concave up, concave down, and inflection points. So for concave up, we have to do the derivative, the second derivative. So for that, you take the first derivative. We'll take the first derivative expression, and then we will differentiate the first derivative. This is our first derivative. We'll take the derivative of that. That also has a denominator, which is x squared plus 3 the whole square. So quotient rule. Again, it is quotient rule. So it is denominator times derivative of numerator minus numerator times derivative of the denominator. So when you do the derivative of x squared plus 3 the whole square, you have to do the chain rule. Right? So it is outer derivative, which is 2 times x squared plus 3 times the inner derivative, which is derivative of x squared plus 3, which is 2x. So that will become 4x times x squared plus 3. So that is the numerator part. Then the denominator is denominator square. So it will be x squared plus 3 to the power 4. So we will pull out a common factor here. So x squared plus 3 is a common factor on the numerator. So we will pull out one x squared plus 3 outside. And also there is a 6 that is also common. Pull that out. So now you are left with x squared plus 3 for the first minus 2x times 2x. So you have 2x times 2x, that is a 4x square times just 4x square. X squared plus 3 has been taken out, minus 4x square divided by x squared plus 3 to the power of 4. We reduce it, it's x squared plus 3, so it will be x squared plus 3 to the power cube to the power of 3. So this will be 6 times x squared plus 3 minus 4x squared divided by x squared plus 3 the whole cube. So it will be 6 times 3 minus 3x squared, if you simplify the like terms, divided by x squared plus 3 the whole cube. So you have a common factor here, which is 3. Can pull that outside, which is 6 times 3, 1 minus x squared over x squared plus 3 the whole cube. So you get that to be 18 times 1 minus x squared over x squared plus 3 the whole cube. Now we have to discuss about the sign f double prime x. Where is it positive? Where is it negative? So in the expression for f double prime x, the denominator, which is x squared plus 3 the whole cube, is always positive. It's always positive. So the sign of f double prime x depends on the sign of the numerator. So f double prime x is positive when the numerator, namely 18 times 1 minus x squared, is positive. This means 1 minus x squared is positive. So this means 1 plus x times 1 minus x is positive. So if you notice here, let's take negative 1 and let's say this is positive 1. So if I give a value to the right of 1, let's say x equal to 2, test point, x equal to 2. Then if I plug in into 1 plus x times 1 minus x, it will be 3 times 3 times 1 minus 2. 1 plus 2 times 1 minus 2. 1 plus 2 is 3, positive. 1 minus 2 is negative. So this is here, f double prime x is actually negative, right, in this interval. Between negative 1 and 1, we will take the test point to be equal to x equal to 0. So what will happen to f double prime x? So it will be 1 plus x times 1 minus x, x equal to 0. So that will be positive. So in this interval, f double prime x is going to be positive. Then to the left of negative 1, if you plug in x equal to negative 2, so you get a negative times positive, that will be negative. So f double prime x will be negative here. So here it is concave down in this interval. In this interval, it is concave up. Then in the third interval, it is concave down also. All right. So we can conclude here f double prime x is more than 0. F double prime x is more than 0 when x lies between negative 1 to positive 1. And f double prime x is negative on negative infinity through negative 1, union 1 through infinity. So in this interval, it is concave up. In this interval, it is concave down. So we can write f is concave up on negative 1 through positive 1. F is concave down on negative infinity to negative 1, union 1 through infinity. Right? This is another information about the graph. Now, wherever the concavity changes is the inflection point. So if you write down the inflection point for the graph, the concavity changes at -1 and +1. So x coordinate is plus or minus 1. Y coordinate is f of plus or minus 1. So in this case, as the function is even, f of plus or minus 1 is going to be the same x square over 1, what is a function? X square over x square plus 3. Suppose you plug in 1, so it's 1 square over 1 square plus 3, 1 over 4. So irrespective of the x coordinate, plus or minus, the y coordinate seems to be always positive because the function is an even function. So it is plus or minus 1, 1 over 4. Those are the inflection points. So we have every information that is needed for the graph. So we will be able to sketch the graph now. We have to put all these things together before in the graph. One thing here, when we said f is decreasing on the interval -infinity to 0, then f is increasing on the interval 0 through infinity. When the graph decreases and then increases, that will be a valley, or that will be a local minimum. The local minimum occurs at 0 here because that's where the change occurs. So that is the x coordinate. The y coordinate is f at 0. The y coordinate is f at 0. If you plug in 0 into the original equation, you get 0. So x coordinate is 0, y coordinate is 0 as well. So that means the local minimum occurs at the origin for the graph. We will include that information also in the graph. And then you can sketch the graph the way I have shown here. So it's x-axis, y-axis, and y equal to 1 is the horizontal asymptote. The graph is increasing on the interval -infinity to 0, increasing on the interval 0 through infinity. The local minimum occurs at the origin, and it is concave. It's concave up in the interval -1 to 1, and it is concave down from -infinity to -1 and 1 through infinity. And the inflection points are also shown in the graph. So this is a comprehensive graph of the function using calculus techniques. Hope this video helps. As I said earlier, see my rest of the problems in this additional set of problems in the section video for section 4.4. And then I will be doing the next video. Watch my next video on 4.7, which is optimization. Okay.